Okay, points of discontinuity. So the other day when we were looking at the idea of asymptotes, everything fell from the denominator. The reason why we have an asymptote is because there's a 0 in the denominator, which I can't have. I can't divide by 0. So what we're looking at this time is sometimes the discontinuity is not a curve. Sometimes it's an actual gap in the graph. And we're going to look at what type or why there's this type of discontinuity. So if we look at these two functions, we have f of x equals x squared minus 4x plus 2 over x minus 3. And then we have g of x, which is x squared minus 4x plus 3 over x minus 3. So it says state the non-permissible value for each function. What can't f of x, what can't x equal in f of x? 3. And what about g of x? 3. So the non-permissible value is 3. If x equals 3, I'm dividing by 0, which is not allowed. So we're going to use our graphing calculator to graph f of x, and then we'll sketch it on the grid that's below. So we have y equals, my calculator's stuck. Okay. So y equals x squared minus 4x plus 2 in brackets, and then divided by bracket x minus 3. And then I graph. And I see where x equals 3, there's my vertical asymptote. So I'm going to take this graph and I'm going to sketch it down here. So where x equals 3, there's my vertical asymptote. And the graph approaches it on both sides. And there's no horizontal asymptote this time, because the degree of the top is bigger than the degree of the bottom. So up above, we're asked to state the asymptote of f of x is equal to x equals 3. So a student assumes that the graph of g of x is going to be very similar, that I'm going to have this asymptote where x equals 3. So if we use the graphing calculator to graph the second equation, and the second equation is x squared minus 4x plus 3. So I changed the 2 to a 3. When I press graph, what do you see?
Straight line.
A straight line. So what shape does the graph appear to take? It appears to be a linear function, right? Does the graph have a vertical asymptote? Do you want to press pause, Jessica?
Okay.
Yep. Okay. So the graph appears to be a linear function. Is there a vertical asymptote? Nope. But is there a point, or can the graph be continuous? Does the graph exist for all values of x?
No.
No. There's a spot in the graph that does not exist. When x equals 3, it's undefined. So when And we can see this discontinuity if we press zoom and then 4 for decimal. What do you notice now?
There's a little.
There's a little spot, there's a little gap. And where does that gap happen? When x equals 3. So I get this straight line that goes through, and when x equals 3, I'm not sure what the value of y is at that point, there's this stop, or this hole in the graph. That hole in the graph is what we call our point of discontinuity. So let's look at another example. If we have the function a of x, which equals x plus 2, and b of x, which equals x squared plus 3x plus 2 over x plus 1. What is the domain of a of x? What are my possible x values? What can x equal?
Anything but -2.
Can it equal -2? Can this equal 0?
Yeah,
There's no denominator, so can it equal
Oh.
-2?
never mind.
So are there any restrictions? No, x could be anything. What about b of x? What do I have for a domain for b of x?
X can equal -1.
X can equal -1. But could equal anything else. Okay, so if we graph x plus 2 on our zoom decimal, so x plus 2, there's my linear function. So I can sketch that. When x equals -2, I've got a 0. When x equals 0, I've got a positive 2. Sketch that in the right spot. And there's my line. If I sketch b of x, I get x squared plus 3x plus 2 divided by x plus 1. What do you notice this time? Okay. I still have this point of 2, -2 and 0, and 0 and 2. So I still have those 2 points. But then I have this hole, like Rachel said, when x equals -1. If I slid this line over to this graph, would they be the same? What's the difference?
One has a restriction.
One has the restriction. So the difference between the two graphs is in b of x, when x equals -1, there's a point of discontinuity. So we're going to take a look at b of x. X squared plus 3x plus 2 over x plus 1. Can we factor the numerator? Two numbers that multiply to 2 and add to 3?
X plus 2 and x plus 1.
X 2 and x plus 1. Now that I've written it in factored form, do I have any common factors that I could cancel out? X plus 1s. So that leaves me with x plus 2, with the restriction, however, that x cannot equal negative 1. And that restriction comes from my original function, my original equation. So this right here is the reason why the two graphs look the same. Because in simplified form, they are the same graph. The difference being b of x has that restriction which creates the hole. So we can determine the coordinates by placing the non-permissible value into the equation of the line. This is the equation of the line. So if we substitute, so b of x simplified is x plus 2. If we put in the non-permissible value of negative 1, I get negative 1 plus 2, which equals 1. So then my point of discontinuity is negative 1 and 1. That's how we find points of discontinuity. We simplify the equation and we put the non-permissible value into that simplified equation. So if we have the function g of x equals x squared minus 4x plus 3 over x minus 3, this is from part 1. If we were to factor this and simplify this, we could then find the point of discontinuity. So two numbers that multiply to 3 and add to negative 4. So negative 1, so x minus 1 and x minus 3. What factors do I have in common? So I could cancel those factors out. So g of x simplifies to x minus 1. However, x cannot be equal to 3. Because when x equals 3, in the original equation, I get a 0. So then to determine the point of discontinuity, I substitute 3 in for x. And I solve, which gives me 2. So then the coordinate is 3 and 2. That gives me the hole in the graph. So the top of the next page outlines that. If the numerator and the denominator have a factor in common, then the rational function is going to have this point of discontinuity, this hole. We represent it with an open circle. So if you remember, when we were solving inequalities, the open circle meant it does not include. So the open circle on the graph still means the same thing. It does not include that portion of the graph. To find the coordinates of the point of discontinuity, we factor the rational expression, simplify by canceling out the common factors, and then substitute the non-permissible value of x into that simplified form. Unless we are on zoom decimal, or maybe multiples of zoom decimal, or a zoom in, you will not actually see the point of discontinuity. So you have to be aware that it exists based on the restrictions of the original function. So that's the first thing that you should be looking at whenever you see a rational function, is what is the non-permissible value. Because if you go and put it into your calculator knowing that there's a non-permissible value, and if you can't see it, then you know a point has to exist. Okay? So it says consider the rational function x cubed minus 7x plus 6. So we need to factor the numerator. And because this is a third degree, how many factors can I get? 3 factors. So the degree tells me how many factors I should be able to get. So if we go to factor this, we can use our remainder theorem from the last chapter. So what I would do is I would let y1 be equal to this x cubed, so x to the power of 3 minus 7x plus 6. And then I would go to my table. And if my table's on ask, the values that could be possible factors are going to be anything that is a factor of 6. So positive and negative 1, positive negative 2, positive negative 3, positive negative 6. So I'm going to start off with positive 1, which gives me a 0. So 1 is a possible factor. Or sorry, 1 is a possible 0. So then I can use my synthetic division to help me divide. So I have 1, 0, negative 7, and 6. Why the 0?
There's no 2 power of 2.
Right. I have no x squared, so I still have to hold the place. Remember the synthetic division? We bring down the first one, and then what do I do with the 1 and the 1?
Multiply them.
And then add, I get negative 6. Multiply, I get negative 6. And there's my 0. So now I've shown that 1 is a 0. So x equals 1, which means that the factor would be x minus 1. So there's one factor. That leaves me with x squared plus x minus 6 times x minus 1. Oops. Sorry, equal to f of x. That's equal to x cubed minus 7x plus 6. So I've gotten one factor. Now I can factor that quadratic. If I go to factor x squared plus x minus 6, what do I get?
X plus 3 and x minus 2.
So there's my factored equation. So then f of x equals this x plus 3 times x minus 2 times x minus 1 over x minus 1. My x minus 1s are common factors, which means they cancel. And I'm left with x plus 3 times x minus 2 with the restriction that x cannot equal. What can't x equal? 1. So to determine the point of discontinuity, I'm going to substitute 1 into that simplified equation. So I'm going to substitute into the simplified f of x. So I get 1 plus 3 times 1 minus 2. So 1 plus 3 is? And 1 minus 2 is? And 4 times negative 1 is is -1 or -4, sorry. So then my point of discontinuity, which I'll abbreviate POD, is 1 and -4. Question C, when it says state the zeros of the function, that's the zeros of the simplified function. So what are the zeros of this function right here that I'm circling? -3 and 2. So if I was going to sketch parts of this, there are certain parts that I could sketch. I know that I have a 0 at -3 and at +2. I also know that if x equals 0, in my original equation, I would get 6 over -1, which would be -6. So I know that I have a point of 0 and -6. And then I also know that I have this hole in the graph, which is at 1 and -4. And then I could use my graphing calculator to help me put in the other pieces. And what I get is a graph that looks something like this. So I get this quadratic that has a hole at 1 and -4. So these are the questions, 1, 3, 6, 11, and 12. So the last class example we won't do because it's outside the scope of our program of studies.